Good day, madam. I'm Lom Yuen, representing Group 4, and I'm thrilled to guide you through our assignment. Allow me to introduce you my team members, Lim Ming Quan, Gan Ching Zan, and Lim Kai Sheng. Today's presentation centers around program execution expression, focusing on the intricacies of postfix notation, stack diagram, and the 0, 1, 2, 3 address. Without further ado, let's dive in. Firstly, let's understand the original expression. X equals E divided by A plus K multiplied by D plus Y times J divided by S minus G minus B times P. This expression involves various operations like addition, subtraction, multiplication, and division. To compute this effectively, we need to follow a specific order and this brings us a concept of program execution expression. Now let's transform this expression into postfix notation. In postfix notation, operators come after their operands, making it a bit unconventional at first glance. But it simplifies how we interpret and evaluate mathematical expression. Here's how our expression transforms step by step. So first of all, we will use this, the A plus K, it will be transformed into AK plus. The plus will be moved to the back. And later we can move forward and the divide will be moved to the back. So it will be EAK plus divide. And later we will also move the multiply to the back of the D. So it will transform to EAK plus divide, D multiply. Later it will change this Y times J into YJ times, moving the multiply to the back. And later it will do the same and move the back of the minus to the back. Later, it will move this divide into the back as well. So it will be Yj times with Sg minus divide. And then we can finally combine this together by putting this plus into the back of here. Later, we will transform this B times P into BP times. And finally, this minus will be moved to the back and the postfix notation is complete. And when the postfix notation is complete, we will move on to the stack diagram. Now let's delve into the intricacies of the stack diagram to gain a detailed understanding of its functionality. The stack diagram is a valuable tool that not only aids in comprehending the expression but also simplifies the process. I will illustrate its working using the table displayed below. We will first add the E to the stack diagram and later the A and K. The A and K will be combined together because they are in one bracket, and when the D is combined, it will be combined together because they are in one bracket together. So later it will be Y times J, as you can see here, and they will be combined, Y times J. And later it will be the S minus G right here, and it will be combined with the S minus G. And later it will be combined into another expression and will be combined into a new expression. And continuing, B times B and P will be formed to B times B, P, and combined into a new expression here. And after this expression is done, it will be blank. Following that, let's shift our focus to the zero address. As per our routine, I'll provide a comprehensive explanation of its functionality. And simultaneously, you can observe a practical example displayed on the screen. So, how a zero address machine works is that it uses the postfix notation that we did earlier. And we will be using the final one, which I have shown an example here. So we first push E, push A, push k, which is all right here. Then we add and divide, add, divide. Then we push d, then we multiply, which is here. Then after that, we push y and push j, and we multiply y, j, multiply. Then push s, push g, sub, push s, push g, subtract. And we later divide, add, push b, push p, which is here. We divide, we add, push b, push p, then we multiply and we subtract it. We multiply and subtract it, and pop x, which means we put all of these into the x variable. So all of this will be stored in the x, and there you go, zero address machine instruction complete. As for the first address, it doesn't work like how zero address work. It doesn't use the postfix notation. So you first load the B into the AC, the temporary memory. After you load to the temporary memory, you will multiply by P, which is B times P, and it will store in the temporary memory again. And once after it says store R1, the B times P will be stored in the memory called R1. Then it load S into a temporary memory again and sub G, S minus G, and store into the R2. And later it will load Y and store in the temporary memory and load multiply by J, and it is still in the temporary memory. After that, it divide by R2. Let's look at back. What is R2? R2 is S minus G. So y times j divided by R2, which means y times j minus by S minus G, and it is still being stored in the temporary memory until it is stored back in the R2, and so the R2 memory is overwritten, and it is now storing y multiplied by j divided by S subtract G. After that, it will load A into the temporary memory, continue, A add with K, and it will be stored in R3. After that, it will load E and store in the temporary memory again and divide with R3. R3 is A plus K. So E divide with A plus K and store in the temporary memory again. Multiply by D, store in the temporary memory, and now you add R2. Remember, R2 is y times j divided by S minus G. So now this plus with this, and now it's stored in the temporary memory, and later is sum with R1. R1 is B times P, and until the end, it will store in the X. And the first address is finished. So now let's proceed with the two address machine instruction. And same as usual, we will be using the same program execution expression. We'll begin by moving the B into the address R1 and multiply B with P. After that, we'll move S into address R2 and subtract it with G, so S minus G. Now we'll store Y into the address R3, multiply with J, Y multiply by J, store in R3, and after that, it will divide R3 with R2. So Y times J divided by S minus G, and will be stored in the R3. Later, it will move A into R4, add A with K, and this is the result. And later, we'll move E into the address X, which is the current address, and multiply X with D. No, and divide X with R4 first. So E divide with A plus K and multiply with D here. And we will finally add x into R3. This is x, and this is previously the R3, y times j divided by s minus g. And finally, we will subtract with x with R1. Remember, R1 is b times p. And finally, the expression is finished. For the 3 address machine instruction, we will be using 3 address. We will multiply b and p and store in the address R1, like so. And later, we will subtract s minus g. We will subtract s with g, store in R2. Multiply y and j and store in R3. And divide R3 with R2, which also means y times j divided with s minus g, and store in R3, like so. And later we will be adding a and k and store it in the address R4. And now we will be using the address x as we are reaching to the final stage. So e will be divided with R4, which is also known as a plus k, like so. And after that, we will be multiplying x with d. X previously is e divided by a plus k, and now it will be multiplied with d and will be stored in x as well. X later will be added with R3, also known as y times j divided by s minus g, and will be forming this expression. And after that, it will store in x, and we will use x subtracting with R1, also known as b times p. And here we go, the expression is finished. In conclusion, I extend my heartfelt gratitude to my lecturer for generously sharing her time and expertise. Thank you for guiding us through the nuances of computer architecture. And to my dedicated teammates, thank you for the unwavering support and collaborative spirit throughout this journey. Your contributions have been invaluable, making this exploration both enlightening and enjoyable. Together, we've unraveled the complexities of program execution and addressing schemes. Let's carry this newfound knowledge forward, appreciating the intricacies of computing, and thank you all who joined us on this insightful adventure.